Okay. 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 All right. We'll get started. So, so new people, thanks for coming. I am posting the lectures on Teams, links to videos of lectures, and I also have a secret channel on YouTube, and I post the videos there. So the first two lectures of the class were Introduction to Emergence, and those are on YouTube already. So we're now starting week 2, and we're just getting started. So I'm going to recap last week's lecture, and then we'll move into the new stuff. So what did we do last time? Oh, one more thing before we get started. Anybody who's starting new, even if you're an auditor to the class, you're just an observer, that's perfectly fine. But send me an email, let me know, so I can make you an observer on the website, so that then you can look at Canvas, you can get announcements, you can also access Teams, where we have discussions and lecture notes and errata and things like this. All right, so last time we introduced the Ising model for classical electronic spins. So we have a system of spins on a lattice in d dimensions, n spins, and the spins can be either plus or minus 1. And the Hamiltonian is just what I've written here in the middle of the screen. So what you have here is the external magnetic field interacting with the spins. So that's the first term. And if that term was all that there was, that would just tell you that I have a bunch of spins. They don't interact with anything else, but they interact with the external magnetic field, and they lower the energy by lining up with the magnetic field. And so this is basically a bunch of dipoles in an external magnetic field, which is even 4. All of that is something that you have learned in a classical statistical mechanics class, elementary class, or graduate entry level class. The next term is the interaction between spins. You know it's an interaction because now the energy depends on a spin at site I and a spin at site J. So it depends on both of their configurations. So that's why we call it an interaction. And J is the ferromagnetic exchange coupling, which if you look in my lecture notes on basic statistical mechanics, I derive how J is related to the wave functions of the electrons on neighboring lattice sites. So in Teams, I posted for you my lecture notes for my graduate statistical mechanics class, which I've never taught here, but which I used to teach at Illinois. And it teaches you all sorts of things that you won't find in any other statistical mechanics class. And I gave you in Teams the section numbers to look at to give you the basic introduction to the things we're doing in this particular class. Okay, so that's the Ising model. That's the first thing that we introduced. The second thing we decided to do was to look at the symmetry of the Ising model. So this class is all about broken symmetry, spontaneous symmetry breaking. This is the class where you learn about that and all its implications. So we started off by looking at a very simple symmetry transformation. And the idea was this: if I know the energy of the system, which is what the Hamiltonian is, and I tell you the configuration of all the spins, S1 up to Sn, and I tell you what the magnetic field is there a symmetry that I can make a transformation of the spins so that the Hamiltonian stays invariant? And if you look at this Hamiltonian, you can see that if I take every spin and flip it from +1 to -1, which we call time reversal symmetry, what will happen then is the two minuses here will become a plus, so that won't change. But the first term with the magnetic field will change its sign because one of the S has gone to -S. So if you then change the sign of the external magnetic field as well, then it changed the Hamiltonian back to where it was before. And so what we end up with is the fact that the Hamiltonian is invariant under a simultaneous spin flip of the spins, time reversal symmetry as we call it, and a change in the direction of the external magnetic field. We call it time reversal symmetry because you have the idea that the spins are flipping. So if a spin is up, then previously it was down. So we've kind of reversed the direction of time. But that's complete nonsense, because we're talking about equilibrium statistical mechanics here. And in equilibrium statistical mechanics, everything is in equilibrium, so there's no time. It's just a name that people give it, but it's a very misleading name. So sometimes people call it spin flip symmetry. Sometimes people call it Z2 symmetry, because it's the symmetry of a permutation group of two objects. So it doesn't matter what you call it, that's what it is. This symbol over here, this upside down A means for all. So this means take all the spins and put a minus sign in front of it. Then what we decided to do was look at how do we measure order. And the way we measure order, this is meant to be a magnet. If it's a magnet, it's supposed to stick on the wall of your refrigerator. That's what a magnet, on the door of your refrigerator. That's what a magnet is. Stick it on the door and it stays there, okay? It's magnetic. So how do you know if it's magnetic? Well, magnetism is caused by an imbalance in the number of spins pointing in one particular direction. So we make an order parameter, a measure of order in the system. And the measure that we naturally choose is we count how many spins point up minus how many point down. And the imbalance in that number divided by the total number of spins is the magnetization per spin, and that's defined down here at the bottom. And so that's the thing, that if it's non-zero, it means that it will stick to the door of your refrigerator, it's magnetic. If it's zero, then it's not magnetic at all, and it will just fall to the ground. So that is our measure of order. So then we try to calculate that from the Boltzmann distribution. And I'm not going to go through the calculation that we did. I'm going to do it in a different way in a minute. What we found was that, in fact, we could prove rigorously that the magnetization is exactly equal to zero for all temperatures. Okay, so the magnetization is zero. That says that our model of a magnet actually doesn't work at all. It doesn't give us ferromagnetism. We didn't answer the problem of where does magnetism come from. What we expected was shown here in the middle of the page. So what we expected, if at least I haven't any external magnetic field, so as long as I'm looking at the situation where there's no external field, what we would expect is that if I'm at high temperatures, there will be no magnetization at all. Why? Because the free energy of the system is the energy minus T times the entropy. And as the temperature gets very high, what the system can do to minimize the free energy is maximize the entropy. Maximizing the entropy means maximizing the number of configurations that corresponds to a particular state of the system. Obviously, if the system has no magnetization, as many spins point up as down, there's a huge number of ways that can happen. If this, on the other hand, if the spins are all pointing up or they're all pointing down, for each of those states, there's only one way that can happen. So entropy is maximum when the spins are all pointing in random directions. So at high temperatures, the free energy gets minimized at high temperatures by maximizing the entropy. And that gives the minimum free energy at high temperatures. And so that means that that's why we would get zero external magnetic field. On the other hand, at low temperatures, the energy, when the spins all point in the same direction, their cooperative interaction, the cooperative interaction being this term here, the collective interaction between the spins, when that term is minimized, then the free energy itself is minimized. So at zero temperature, minimum U gives minimum free energy. And at low temperatures, we can forget about the term T times S. And so that tells you that at low temperatures, the spins will all point in the same direction, either up or all down. And so we would expect the curve shown on the right that the magnetization will start off per spin will start off at 1, gradually go to 0. But the big surprise is, and this is the surprise that we will figure out why it happens, is that instead of just going to 0 gradually as you get to infinite temperature, it actually drops to 0 at some finite temperature, maybe 1,000 degrees or something like that. And then it's exactly 0 thereafter. That's not what you would have expected, but that's what's true because of the way statistical mechanics works, and that's what we actually discussed in the course last quarter. Okay, so that's a review of last week's lecture. I also want to point out that in Teams I put a channel to review the basic concepts of statistical mechanics, so that is shown here. And in this post on Teams, I've mentioned to you down here at the bottom which are the particular sections in my lecture notes to look at to get a basic understanding of some of the things in, say, the Ising Hamiltonian, if they are unfamiliar to you. Okay, so now what we're going to do today is we're going to figure out why it is that the Boltzmann distribution didn't work. Okay, because the Boltzmann distribution is supposed to work. How come it failed? So that's what we're going to do now. So let's go to that. So what I'm going to start off by doing is I'm going to tell you a story which is basically summarized by the phrase ergodicity breaking, and that's in section 2.91 of my renormalization group book. So whenever I write down numbers like this, they correspond to the section in my book on renormalization group and phase transitions, and I will later give you references to my own lecture notes for this course, which are also on the Canvas website. So what I want to do is now think about what I just showed you from the point of view of probability distributions. So let's go and do that. Okay, so what is the Boltzmann distribution? The Boltzmann distribution answers the following question. If you tell me the state of the system, and by the state of the system, I mean what is the configuration of every spin in the system, so the set of all the spins, SI, what is that probability distribution? And what Boltzmann told us is that this is equal to e to the minus beta times the energy, the Hamiltonian, and then it's normalized by the partition function of the n spins, and the partition function, as we wrote down last time, is just the sum over all the spin degrees of freedom of e to the minus beta h. So that's what the Boltzmann distribution is, and then what we did last time was we said, well, let's set h equal to 0, and then when h is equal to 0, you can see that the Hamiltonian is just minus j si sj, and I and j are nearest neighbors. That's what this symbol means over here. And you can see from this that this Hamiltonian without the external magnetic field has the symmetry h of minus si is the same as h of plus si, because the two minuses make a plus. So what that means is that the probability distribution for the spins is an even function. And so when I compute the magnetization, so let's suppose I were to compute the expectation value of spin Si, so that is 1 over, well, let me write it like this. This is the trace over the spins. So this thing here, I'm using the word trace. So this is the trace of the spin Si times the probability of all the systems, of all the spins. So that's what I mean by the expectation of the spin at site I. I take the probability distribution for any configuration, that's P. I then take the thing I want to compute the expectation value of, which is Si, and then I sum over all the degrees of freedom. And you can see that because this function is an even function, and this thing over here is an odd function, then an even times an odd function, when I average over all the possible values, that's going to give me that this thing is identically equal to 0. So that's the reason. So we conclude that the probability distribution cannot be the Boltzmann distribution. So, well, that sounds kind of crazy. It's certainly at least not for T less than Tc. So we do know that in the real world, there does exist ferromagnetism. So we know that there is a critical temperature. That's a statement of empiricism. So if we're going to explain that, it's got to be that the Boltzmann distribution isn't the right distribution. So what went wrong? Well, it was pretty easy to see what went wrong. Here is our configuration space. And I'm going to sort of divide this configuration space up into states where the magnetization is positive and states where the magnetization is negative. And then if I have a state in this space, so here is the state which I'll call A. So at this point in this space, this corresponds to a configuration of all the spins, which I will call SA. We know that there's another point in this space, which I'll call B, and for this one, the configurations of B, every spin is reversed. And so what happens is when I sum over all the spins, I can, for every configuration where I compute the magnetization, summing over all spins, for every configuration where m is greater than 0, there is another configuration with all the spins flipped, and m is negative. And so when we sum over all of them, that's of course why we get that m is equal to 0. So the solution to this, to figure out the solution to this problem, let's have a look at what happens when we add an external field. So let's go and do that. So what we're going to do is we're now going to put back into the Hamiltonian the term that we missed here. So what we did just now was we just considered this case without an external magnetic field. When you have an external magnetic field, you also have this extra term that you can see here on the left-hand screen, HSI. So we're now going to put that term back in. So what happens when we put that term back in? So now that's going to bias. So H non-zero will bias the probability to be in the direction of the field. By that, what I really mean is that the probability of A is now no longer going to be the probability of B. the two states. They look equal and opposite, but one of them is pointing down with respect to the external magnetic field, and one is pointing up with respect to the external magnetic field. So this is going to be true because of the term minus h sum over I equals 1 to n si. And this symbol here, when I write down this symbol, I mean because. Okay, so let's ask ourselves, well, what is going to be the probability of PA over the probability of PB? Well, you can see that the way that this term comes into the Hamiltonian, this term over here is just minus h, and then it's times n times the magnetization, because the magnetization is the sum over ISI divided by n. So therefore, the sum over ISI is just n times the magnetization per spin. So this the ratio of these probabilities, everything is the same except for this term, and so we're going to get e to the minus beta minus h n times m. That's for the state A, and then for the state B, now the spins are reversed, so it's going to look just like that. And so the ratio of these two things is e to the 2 beta h n m. Okay, so those two things are biased because when the spins point down, they're in a different direction than the external magnetic field, and if they point up, so states A and B are no longer equivalent. Okay, now what we're looking for is in equilibrium thermodynamics or equilibrium statistical mechanics, we are interested in taking the limit n goes to infinity, the so-called thermodynamic limit. And then the other thing that we're going to do here is I'm going to assume, without loss of generality, that h is positive. So if I take that limit, then what you can see happening is that PA over PB is going to go towards infinity. So in other words, PA is going to be much, much greater than PB as I take that limit. And so another way of saying that is to say then that PB becomes much less than PA. And that's going to be true as n goes to infinity, even if h is going to 0 and is vanishingly small. So I'm making the distinction here between taking an external magnetic field and making it equal to 0, and taking an external magnetic field and making it very small. So even the external magnetic field is 10 to the minus 15 GeV. Okay, very, very small number, even smaller than the Earth's magnetic field. When I take the n going to infinity, that's going to go to infinity, and this thing is still going to go to infinity. So the limit as h goes to 0 and the limit h equals 0 are not the same, and so what this means is that as I take that limit, in this limit, for any h that is 0 but a tiny little bit, basically what's going to happen is that PB will equal 0 and PA will be non-zero. So what that means is that it's not true that we have a Boltzmann distribution over all states. We have a Boltzmann distribution only over the states only over the states which are in the direction of the magnetic field. So conclusion of this argument, I'm going to state this again in a minute. So the conclusion is that the Boltzmann distribution over all states is not correct in the limit that h goes to 0 plus and n is going to infinity, in fact, what you have is that PB is equal to 0 and PA is equal to e to the minus beta h over the partition function. So you have a situation where I can think of the system as looking like this. Here is my configuration space as I had before. Here are the states with positive magnetization, and here are the states with negative magnetization. And so what has happened, in order for there to be a non-zero magnetization, is that in this region here, I have the probability distribution for all the spins is non-zero. Here, it's exactly equal to 0. And in fact, this non-zero value is the Boltzmann distribution, e to the minus beta h over z. So that is one particular thing that can happen. It can be either this or it can be the other way around. And I'm just going to write this very briefly. So here, P is non-zero equals Boltzmann. And here, P is equal to 0. And either one of those things can happen. And which one happens depends on the sign of the external magnetic field that you apply. If the external magnetic field is plus, then you'll get the top one. If the external magnetic field is negative, but going to be 0, then you'll get the bottom one. So those are the two possible outcomes for the probability distribution. So let's see what that means in terms of what you would measure in an actual experiment. What would you measure in an experiment? So what you would measure is this. The only thing you know how to do in an experiment is I apply an external magnetic field to the system and I measure the magnetization per spin n. And I can do that as I vary the temperature. So let's ask what happens then when I do this at very high temperature. So the temperature is certainly above Tc. So what's going to happen is this curve. You can compute it exactly, and I'm not going to show you that. This curve will look like so. It's a curve that goes through the origin, and this is what you would get if I had a system for temperature greater than Tc, and even n goes to infinity. Okay. On the other hand, if I have a system below Tc, then what happens is I get something like this. I apply the magnetic field, that gives me a magnetization. I lower the temperature, and as I've lowered the temperature, I said it wrong. Let's start off again. Start off with a low temperature and apply the external magnetic field, big magnetic field. Then, as I lower the external magnetic field, I will come down this trajectory here, and even as I make the external magnetic field vanishingly small, there will still be a net magnetization left. That is called the spontaneous magnetization. If, on the other hand, I'd applied an external magnetic field which has a negative value, as I lowered the external magnetic field, I would have got the curve shown over here. So this is what I would get for T less than Tc, H going to 0 from below. This is T less than Tc and H going to 0 from above. So this is H going to 0 plus or minus. So this is This is what spontaneous symmetry breaking actually means. Now, sometimes when you hear people talking about spontaneous symmetry breaking, they'll present it in a very confusing way. What they'll say is, here's spontaneous symmetry breaking. I have a field. Let's say it's a Higgs field in a high energy physics, or it can be a magnetic moment in a condensed matter system, or it can be the order parameter in, say, superfluid helium. Above a particular temperature, this can point in all sorts of random directions, so it has very high symmetry. But then you go to low temperatures and magic, the spontaneous symmetry is broken. So the symmetry breaks spontaneously, and then all the spins point in this direction. So your Higgs field points in this direction. Your order parameter in liquid helium-3 points in this direction. Your order parameter in a Heisenberg ferromagnet points in this direction. It just magically chooses a direction to point in, and that's the idea that the system had a symmetry at high temperature where it could point in any direction, and then at low temperature it chose a particular direction, pointed in that direction, and therefore broke the symmetry that it had. That's the idea. That's what spontaneous symmetry breaking means. It's complete nonsense, okay? That is not what happens. What happens is what I'm showing you here on the screen. The reason why this doesn't happen in real life is because the system will order, but over here it might order in this direction, over here it might order in this direction, over here it might order in this direction, and you will get domains. And those domains will then, they won't all go towards the same configuration. Actually, where those domains meet, you'll get a topological defect. And what will happen is, if you're, say, talking about, say, the Higgs fields in grand unified field theories, talking about cosmological phase transitions early in the universe, what happens is where different regimes meet, different directions of the order parameter, you get a topological defect, you get a cosmic string, you get a quantum vortex line, you get a dislocation, you get these other configurations which are topological. And we're going to talk about those in this course. So this picture here is what is really happening in spontaneous symmetry breaking and the emergence of order. This is always what happens. So let's write this down in an even different way. Another way to write it is in terms of the scaling with system size. So let's talk about that. So in order to, so I want to talk now about the thermodynamic limit. Now, in order to make this conclusion that I've drawn here on the left-hand page, the idea that the Boltzmann distribution is only in one part of the configuration space, it was very important that we took the n goes to infinity limit. Everything that I said in this argument says for this to work, you have to have an infinite system. You got a question, Srijit?
Yeah. So it's exactly opposite. N equals infinity, right? But you said like there could be domains to how do I make sense of that? If I have if I phase transition, I would expect the whole system to point in one thing. Can I understand domains?
I'm going to talk about. So the question is can you say a bit more about domains? And the answer is yes. It's not going to be that everything points in the same direction. Okay.
Yeah, but why would a domain phase transition? Because finite systems don't phase transition.
We'll talk about that in a few minutes. Okay. So how the domains order and so on, those are kinetic processes, and there's also a question about thermodynamic limit. I'm going to talk about that as well in a few minutes. So remember the question and come back to me if I don't answer the question in a few minutes' time. Okay, but all of this argument assumed that we take the thermodynamic limit. So if we don't take the thermodynamic limit, if I don't take the limit n goes to infinity, I just keep n big, 10 or 100 or whatever is your definition of big, then eventually there will become a field value h. small enough so that then the system will then no longer be biased in the direction where the magnetization points up or points down. So what will happen if n goes to infinity is this graph is going to change. So let's draw what this graph will look like. So I'm going to draw H, I'm going to draw M, but now what I'm going to do is I'm going to draw it for finite system size. So let's draw the same curve I have over here. So this is t greater than tc. Let's say n is less than infinity, and I take h going to 0 plus or minus. That curve stays the same. Okay, and now what's going to happen when I look at the system with a finite n, even quotes less than tc, assuming that there's a tc exists? Well, if n never goes to infinity, then what that means is the argument I gave you before about why there is no phase transition, that m is always 0, that argument is exactly correct. There's nothing wrong with it. So for a finite system size, m will always be 0 for the reasons that I gave you before. In other words, unless I take the n goes to infinity limit, eventually for 0 external magnetic field, there'll be as many states with positive as negative, and so it'll average out to be 0. So then what will happen is this curve will look something like this. So let's say that this is for, say, n is equal to n1, and n1 is, say, 100 or something like that, but it's definitely less than infinity. Okay, so it will still go to 0, and so there will be no magnetization. Now let's suppose I do the same thing, but now I'm going to make it n is n2. n2 is bigger than n1. So then what's going to happen is it's going to go down like this, and you'll think it's going to go towards a non-zero value of m, but then it'll, at the last minute, it'll come down like this and go like that. So this curve, the green one, this is n is equal to n2, which is greater than n1. And so what's happening is that for any finite n, I cannot have spontaneous magnetization. There is no order. But as I take the n goes to infinity limit, then I get this curve eventually will approach the one for n equals infinity. So as I make n3 greater than n2 is greater than n1, etc., the curve of m as a function of h will approach the one at the top. One at the top, meaning this curve over here. So that's what's actually happening. Okay, so this all seems very, very subtle, and it is. But this is, when we're looking at understanding order, we have to understand limits in a very particular way. Okay, now I want to add one more point about this. I want to draw this picture that you've seen now a few times. M is greater than 0, m is less than 0, and I want to now draw what we think is happening to the system when you're doing statistical mechanics. So when we draw over there on the left-hand side, when we write down the phase space like that, and we say the probability is 0 in the bottom half of the phase space, where m is less than 0, and is non-zero above it, in order to have the Boltzmann distribution apply at all, we assume that the system is ergodic. Okay, what does ergodic mean? Ergodic means that when we look at the basis of statistical mechanics, what we're assuming is that the system is due to fluctuations, exploring all the possible states of phase space. So ergodicity means that the system dynamics wanders around in phase space like that. And this would be a picture of the system being ergodic, which means wandering. In its configuration space or phase space. And here I've drawn it as just being ergodic in the top part of the phase space. It could actually also be ergodic in the lower part of the phase space. It could be doing, if I'd started over here, it might have gone something like this. So this is another trajectory. This time with m is less than 0. So the system started off with magnetization negative, and it stayed negative, and it wandered around in phase space. That's what systems in thermal equilibrium do, and the probability distribution to tell you about the probability of visiting any point in this phase space is given by the Boltzmann distribution. Okay, this picture is true if t is less than tc. If, on the other hand, we had the situation where t was greater than tc, what would this corresponding picture look like? So suppose I started at this point in phase space. What would you expect the trajectories to look like? So speak up, yeah.
So if it's t greater than tc, I would expect that it would go from m greater than 0 to m.
Right. So what it said was that it's going to be wandering just as before, but now it's going to go equally above around all the states, the m greater than 0 states and the m less than 0 states, because this is what happens when t is greater than tc. Then we know that there is no net magnetization. And so what that means is it samples the states which are positive and the states which are negative with equal time, equal weight. And so it is ergodic over the whole of phase space, not just a subset of it. So this is full ergodicity over all of phase space. And here it is ergodic in phase space, but only over a bit of it, only over a part of phase space. And this fact that it's only over part of it, that's what we mean by ergodicity breaking. Okay, so that's the conceptual picture of how we can get order in a system. Yes.
This is an equilibrium system, does it have time? So how do I think about these trajectories?
So the way you think about it is this. Okay, so the question is, well, there's no time, just as I quoted a few minutes ago. So remember that the whole basis of statistical mechanics is the idea that if I want to compute the average of some observable as a function of time, and I want to do this over a long period of time, so this would be the 1 over t, the average of this variable from 0 to, let me call this, let me call it t star, so you don't think, go away. Oh man, I hate this. Right. Okay, let's try this again. Okay, so it's going to be 1 over t max, the integral from 0 to t max. That's a time, not a temperature. dt of f of t, and I'm going to look at this in the limit as the time that I average over goes to infinity. So what I do is I take a variable, I take measurements of how it fluctuates in time. I then compute its average, so I integrate over all of time, but I only measured up to a time t max. If I then take that time going to infinity, that defines for me the equilibrium average of this observable, and this thing, this expectation of f of t, which is this time average, is equal to the probability distribution, the equilibrium Boltzmann distribution of the system, so let's say the SIs, and then over the variables SI. So here now we have an average over distributions, not time average. And here we have a time average. So the whole ergodic hypothesis, which is the base of statistical mechanics, says if I want to do that, what I do, instead of doing the time average, I just compute the average over probability distributions that tells me the density of trajectories in phase space. And then if you go to an elementary graduate level class on statistical mechanics or read my notes on it, we derive what this distribution is, and this distribution is the Boltzmann distribution or the Gibbs distribution. And that's what we prove. So this whole thing is called the ergodic hypothesis. And I haven't stated it precisely, but you can, in some situations, you can prove it. So this is the whole reason we can do statistical mechanics in the first place. Okay, did I answer your question? Okay, great.
So this trajectory is not a real thing.
It absolutely is a real trajectory. Let's suppose I said to you, okay, do me a computer simulation of this. The only thing you can do is you do molecular dynamics, you make your particles fly around in space, and then you measure these things, and then you use exactly this. And you can check that it gets to what you would get from the Boltzmann distribution. So yes, it is a real. Remember, equilibrium statistical mechanics is meant to tell you about the long-time behavior of dynamical systems. And the clever thing about statistical mechanics is that we answer that question not by solving the equation of motion, but by saying we don't need to solve the equation of motion to do this. Here is a hack, a clever trick that enables us to compute what is this probability distribution on the right-hand side, and that's the Boltzmann distribution. Okay, so and then we can then start to ask for time dependence based on this, and we'll talk about that in this course. But yes, this is, you could measure this in an experiment. You're measuring in time, and it gives you the same result. So why do we do this? Because this is easy to calculate, and this is hard. Because I have to solve the equation of motion and then compute the average. Whereas in this one, I don't need to solve the equation of motion. I just need to know what the probability distribution is. And that probability distribution turns out to be universal. It's a large deviation theory if you really want to know. So boom, that's the magic. All right, let's move on. So now I want to talk about what is the mechanism that systems can order. So the next question is, what is the mechanism for ordering? And the answer is, it depends on the dimension. And I want to explain that now. So let's talk about the one-dimensional Ising model. So I've told you a good story so far. Now we're going to see that there's a really interesting twist to the story. So what I'm going to tell you about now is in my renormalization group book, section 2.8.2. Okay, so we're going to look at the one-dimensional Ising model. So let's draw a picture of the one-dimensional Ising model. So here's space, and then I've got my spins. So my spins are, say, this pointing up, pointing down, up, 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 down, down, up, well, whatever, some configuration like that. Okay, so that's a configuration of the one-dimensional Ising model. And the question that we want to understand the answer to question we want to understand the answer to is what is the configuration at t equals 0, h equals 0. Okay, so let's answer that. That's easy because we say, well, here's the Hamiltonian. It's minus j times the sum over nearest neighbors, si, sj, like that. And we're just looking at the energy. So at 0 temperature, the energy is minimized. In equilibrium. And what configuration of the spins minimizes the energy? So we take a look, and we can see that the energy can be most negative if all the spins equal their neighbor, all I and j neighbors. If they're all the same, then SI/SJ is always going to be +1. Whether the spins point up or point down, it's going to be just +1. So I get minus j times n, and so that configuration will minimize the energy. And so what I get is this configuration or this one. Okay, so that's at 0 temperature. That's sort of easy. So now the next question we want to ask is what happens if we slightly raise the temperature? So what's going to happen is that some of the spins are going to flip. Temperature being non-zero means that they are in equilibrium with the heat bath, and so they're seeing fluctuations, and every now and then a fluctuation will come along and make one of the spins flip. So what's going to happen is that some spins will be thermally excited to a higher energy state, and will flip. Okay, so let's have a look at the configuration. So here is space, and now let's draw in the spins. So maybe we will have something like this. All the spins are more or less pointing up. Over here, let's say. And then in the middle here is going to be some rogue spin, which is going to be pointing down. So here's this spin that is pointing down. So this one has been flipped. Okay, so that definitely can happen. Okay, so what? Okay, well, let's ask the question, so what happens if n spins flip and point down? Okay, so I just drew you one over there. Now there's going to be n of them. Let's say n is 100. Okay, so I've got my big system. All my spins are pointing up, and then there's a few here pointing down, up, down, 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 and so on. Okay, so let's suppose we've got n spins that are pointing down, and the rest are all pointing up. So then let's have a look at the magnetization per spin. Is the following. So what I do is I compute following. I compute the total number of spins that are pointing up minus this n that are pointing down, and then the magnetization per spin. I then have to divide by the total number of spins, and then I'm going to do this in the thermodynamic limit. So I take the limit n goes to infinity, and this is equal to what? One. That's right. One. Okay. So n, I said, could be 2 or 10 or something. Suppose n was 100 million. What would be the limiting value? N is 100 million. Big number, right? Would it still be 1? No. Big N is going to infinity. So telling you n is going to infinity, little is on. So let's put n is now 100 million. What will this be?
As long as the length be some fraction of 1. Probably still negligible, and that's still an consistent.
Right. So if n is just a number, you choose a number, whatever number you want, as big as you want. Okay, 10 to the 17. Okay, eventually, as I take the limit as n goes to infinity, eventually this thing will just be 1. Because this n is always going to be much bigger than this. So this tells you that this is always 1, and so what you learn from this is that flipping n spins will not destroy the long-range order. And I'm going to give this word a name, long-range order. We'll see why it's long-range in a minute, but for now, think of it as long-range, meaning it is order going throughout the system. Here at the top of the page, the spins are all pointing up. They're on the left. You go 100 miles down to the right of the page, the spins are still pointing up. There's a few spins in the middle that are pointing down, but overall, over a large scale, the spins are all pointing up. So we call it long-range order. So flipping n spins will not destroy the long-range order that you have at 0 temperature. Okay, so that says, okay, great. According to this argument now, it's the opposite of what we had last lecture. Last lecture, we had that magnetization, ferromagnetism, the spins pointing up is impossible. Now we've got the situation where now we've convinced ourselves that the opposite is impossible, namely that there's always going to be a magnetization of 1. Okay, so what went wrong? Okay, so in other words, weirdly, we now confused ourselves. The opposite of the last lecture. Last time, we said m is equal to 0 always, and that was like, that's weird. Now we've just concluded that m is equal to 1. Okay, so we're now totally confused. Okay, so now let's figure out what's going on here. What we've learned from this is not that m is equal to 1. What we've learned from this is that flipping a finite number of spins in the thermodynamic limit does not destroy long-range order. So what we've actually learned is this. Actually, we just learned that the only way we can potentially destroy long-range order is if we flip a finite fraction of the spins. and not a finite number. Okay, so, and that's going to work the following way. Suppose I have n spins, so I'm computing the magnetization in the thermodynamic limit, just like we did before. I take the limit as n goes to infinity, but now I flip a finite fraction. So now I have a finite fraction, let's call it f, of the spins, and now I divide that by n, and this thing is equal to 1 minus f, and this is less than 1. So if I flip a finite fraction, that does destroy magnetization. So what is our conclusion? So our conclusion, we can state it in this way, that the dangerous fluctuations that destroy long-range order are the ones involving a macroscopic number of spins. And what do I mean when I say a macroscopic number of spins? When I say a macroscopic number, what I mean is that that number, n, is equal to f times n, or in other words, n is a quantity of order n. This thing here we call order n. That's the word, that's how we pronounce it, order n. And what it means is that it scales with n. So we say n scales with big N. That's another way to say it. And what it means is simply that if I take the limit of little n over big N, that is a non-zero limit. It is a fixed fraction. So this is a statement about asymptotics. It could be that little n went as n squared. That would be then we'd say n was of order n squared. So knowing the order, how things vary as you change another variable, that is a crucial thing we need to think about in statistical mechanics. Okay, so now we've learnt that. So far, we just talked about t equals 0. But we don't really care about t equals 0. What we care about is t non-zero. And if I have a non-zero temperature, then that means that we have to worry about entropy. Because remember that the free energy is the internal energy, U minus Ts. And so once T is non-zero, then I have to worry about the entropy. So now what that means is that if I'm a non-zero temperature, then I have to worry about, we don't minimize the energy. What we are minimizing is the free energy. So we have to worry about the entropy. So let's now talk about the entropy. So what we're going to do next is we're going to look at the effects of entropy, and that means when we talk about entropy, if you tell me the state, I have to figure out how many ways I can create that state from microscopics. So when you tell me a state, you don't tell me, well, here's the spin like this, and this one, and this one's up, and this one's down, and so on and so forth. What you tell me is, oh, well, I know half the spins are pointing up. Okay, that's a shorthand. And then I work out how many states are there of the spins, so half of them are pointing up and half of them pointing down. And I can do some combinatorial calculation and work out that number precisely. Okay, so that's what we mean when we talk about macro states and microstates. Microstates are the configurations of every single degree of freedom. The macro states are what we say in words when we convey it to people. Oh, this thing has got a uniform density. This thing has got half the spins pointing up and half pointing down. Okay, so now let's ask ourselves the question is, how many different ways are there to flip n spins? So that's the kind of question that we have to ask if we're going to think about the entropy. So let's we're going to consider that, and we're going to have to supplement that question with the idea that the number of spins that we're going to flip to be dangerous have to be macroscopic number, meaning they are of order n, they scale with the system size. So let's have a look at what we have to do here. So let's talk about the ordered state, which looks like this. All the spins are pointing up. Here, the entropy is equal to 0, because there's only one way for this to be done. What are the number of ways that all spins point up? Well, there's only one way that all spins can point up. Okay, so then I take the logarithm of the number of ways. That gives me the entropy. Log of 1 is equal to 0. So this means that the entropy is equal to 0, and that tells me that the free energy of the system is minus n times j. Where did that j come from? Well, take a look at the Hamiltonian. The j came from here. Okay, every time the spins and their neighbors are pointing up, have the same direction, then I get a factor of n. Sorry, I get a factor of j. How many terms are there like that in the free energy? There's n of them, and so I get nj. Okay. All right. So that's what the system looks like. Now let's ask what happens with a macroscopic number of spins flipped. So I'm going to choose a very simple macroscopic number of spins flipped. I'm going to consider the state that looks like this. I'm going to say, let's make it so that half the spins are pointing up, like this, and then the other half are pointing down, like something like this. And we'll say, so this is a spin I equals 1, I equals 2, blah, blah, blah. This is I equals 365. This is I equals 366, blah, blah, blah. This is I equals 10 to the 6 plus 1. I don't know, whatever you want. And then somewhere in between here, there is a boundary halfway between these two spins where there is a jump in the spin across this boundary. So this is a boundary. In fact, we'll call it a domain wall. Here, on this side of the domain wall, all the spins point up. On this side of the domain wall, all the spins point down. Okay, and so there is a jump in the spin across this domain wall. Okay, so then now what's now going to be the system? So I can do this, and I can do this this is spin 1. We can do this even in the limit as n goes to infinity. Okay, so half the spins actually, let me not give the punchline away. Let me. Okay. All right. So now let's ask, what is the free energy of the system? So the free energy is the internal energy U minus Ts, and the domain wall can be at any site, i.e. at n different locations. So I'm going to ask the question, what is the free energy associated with this domain wall? How much free energy do I cost to create this domain wall? So how would I calculate that? So what I would calculate is the following. I would calculate the free energy where I have a domain wall, I'll call that an interface, minus the free energy when there's no interface, i.e. all the spins point up or all are pointing down. I'm going to call this quantity delta F. So let's calculate what this delta F is. So I claim that it looks like this. It's I've got a whole bunch of spins on the left of the wall. So actually, let me write down the answer and then tell you how I got it. So I claim the delta F is 2J minus KBT log. Okay, so that's what I claim. So let me see, how do I get this? So this term here is the following. Look at all the spins on the left of the domain wall, okay, on the thing on the left. So let's look over here. So then I have minus NJ. Then I've got across this boundary here, the spin flips from -1, minus J, to plus J. So there's a change of 2J. And then if I don't have any spins at all, any flip at all, I have N minus 1J plus J. And so that whole thing gives me 2J. Does it? Right. All the spins on the left, all the spins on the right. So that's half of them. Yeah, it is. Okay, I'm going to ask you to check it. So I'm going to write this out. I'm going to ask you to check this. So this is the free energy over here with boundary and without a boundary. Okay, so now let's ask ourselves the question, what happens in the thermodynamic limit, n goes to infinity limit, for any t greater than 0? And the answer is that delta F will go to minus infinity as n goes to infinity. Okay, because the 2J just stays 2J minus KT log n. T is non-zero, n is going to infinity, log of infinity is infinity. So the free energy will always go to minus infinity for any temperature greater than 0 as I take the limit n goes to infinity. So what does this mean? What this means is that if there is a domain wall in the system, the free energy gets lowered. So the free energy with a domain wall is much less than the free energy without a domain wall. So what that means is, therefore, so that the system likes to make domain walls. So my system looks like this. Here's my system in space. And then what I did, I had a domain wall over here, and I had +1 over here and -1 over here for the spins. And here I had n/2 spins. Here I have n/2 spins, and I'm taking the limit n goes to infinity. Now you're going to say, well, this calculation doesn't make sense because I assumed in doing this calculation that overall here, all the spins point up, and over here, all the spins point down. But if I've just convinced you that the system likes to put domain walls in, then why wouldn't it put domain walls inside the systems on the left and on the right? So in other words, if I started off with this situation, then what would happen is the system would say, well, to minimize the free energy, actually the system on the n/2 spins on the left, actually those ones, I can put a domain wall in there. And in fact, in order to satisfy the boundary conditions, I'd have to put in 2. So I'd put in 2 domain walls over here. And then now I've got domains of all the spins pointing up. So here the spins point up, point down, point up, down, up, down, and there's another one over here, I guess. So what that says then is that I'm going to get a proliferation of domain walls everywhere. As domains split into 2. And so what's going to happen? So what's going to happen then is that eventually I'll get so many domain walls that there'll be no net magnetization. And that's going to be true for any temperature greater than 0, and that's true in d = 1. So what I've just shown you is another amazing thing. So conclusion, in d = 1 and any temperature greater than 0, long range order is impossible in the nearest neighbor Ising model. So last time we concluded that phase transitions never occur. Then today, halfway through the lecture, we concluded that they always occur. And then now we've come to the conclusion that in one dimension, for non-zero temperature, you cannot have long-range order, so there is no phase transition. Okay. So next time, I'm going to make some comments about this. And next time, we're going to see that this is completely correct. But now, if we try to do the same argument in 2 dimensions, we find that it breaks down. It breaks down in a very interesting way, and we're going to discover that you can have long-range order in 2 dimensions. Okay, and that's the end of today's lecture. Okay, so let me stop the recording, and I'll be happy to take questions